All right. Welcome, everybody. I think everything looks right. I'm going to have to be adjusting the screen constantly today because of the different things that I'm going to be showing you. All have a different size in the browser, so I'm going to have to go through, and so you just have to stick with me while I readjust everything for the screen. So welcome on in. Some stuff to go over, and then we'll move ahead with stuff. So for starters, a number of you emailed me about the 6.2 homework, so thanks for doing that. Yeah, there was a mistake there, basically a typo, where I had the month right, but the date, well, actually, I had the date right, but the month wrong, because when you're picking dates from those drop down boxes, and it pulls up, and sometimes it picks, it starts at like the last month instead of where you left off or whatever. June and July, both four-letter words with a J in it. So I just missed that. It was supposed to be July 27th, and it was set as June 27th. So that's all fixed. So no, thanks for letting me know. I don't need to worry about it. You have a few more weeks, about a month, in fact, to get that 6.2 assignment done. So no stress or anything like that. Okay. Let's see. Let me cross these off. So I got this long list to go. 6.2 homework talked about. Okay, so you have time to work on 6.2. Okay, things I wanted to show you. Let's see, what do we got? Oh, student survey. So I have added a survey that you will get points for. So easy points in the class, just a student survey, and it's nothing, it's easy. Basically, at the school we try to make decisions ongoing. We're always making decisions about the classes that we're teaching, and sometimes there'll be groups of students that groups of professors where we disagree about how something should be done. We disagree whether a certain topic should be in a certain class or stuff like that. So we're always ongoing having these discussions about what we're teaching in certain classes, how we're serving our students. Is this the best thing for students? And there's always these kinds of conversations, and they evolve over time. I think that we should make a few changes to the way we teach college algebra in general. I think it would result in better outcomes for students. Some people like kind of the old way of doing it. It's just a disagreement, and there's valid points on both sides of the argument. But I want to give out this survey because I'm going to try to make a case for why maybe we should teach college algebra slightly differently than we do, that I think would actually serve the college algebra students better than maybe we are right now. It's hard to say, but I'm going to try to make a case for it. So what I've put in here is a student survey. I have you put your name in there just because that's how I'm going to go through and give you credit. So in a week, or I forget, what did I say, by July 5th, please have this completed by July 5th. Once that's done, I'm going to go through, and everyone whose name appears on my data list, that in other words, you submitted the survey, you'll get your 10 points for doing this assignment. If you don't do it, then you get 0. But honestly, it's like the easiest 10 points you're going to get in this entire class. So easy questions, nothing personal or weird. Just what is your first name? What is your last name? Again, that's so I can give you credit. What is your major? There's a big, there seems to be some misconceptions about the majors that take this class. Excuse me. So I'm gonna have to go get a water in a minute. Excuse me, I'm all congested. I'm trying to collect some data about what majors people have that are taking this course, because sometimes we design this course to be for one group of students, and I'm not convinced that's who's actually taking the course. And then the last question, do you plan on taking calculus? Like, not like maybe someday you might take calculus. Like, is it part of your plan in order to get your degree that you have to take calculus? So there's a couple different calculuses. There's the one we call applied calculus, which I'm the lead instructor for. So I'm fairly familiar with that class, and I've taught it a bunch of times. There's the applied calculus. That's what most schools call business calculus. Okay, we at this school call it applied calculus because every once in a while a biology major ends up having to take it. But in there it's like 95% business majors, accounting majors, all that kind of stuff that's related to that end up in the applied calculus class. Then there's the engineering calculus. That's if you're going into math, chemistry, physics, engineering. If you're going into one of those, you take like the hardcore calculus series, which is more intense than the applied business calculus. So I'm just asking that question. Do you plan on taking calculus, right? We want to get a good measure of how many students that take this class actually go on to calculus. That will be some of you will go on to calculus, but it'll be a bunch of you are like, oh, I don't need calculus. I just need it for this one requirement, or so that I can get into business calc or whatever. So if you're taking a business or applied calc, please make sure you pick the right calculus, because otherwise that can affect the decisions we made. Or maybe you don't ever plan to take calculus at all. Great, click that. Or maybe you don't know. So if you could just answer those 4 questions, feel free to do it literally right now while I'm talking to you about it. You can go through them, and it'll take most of you less than a minute to fill this out. First name, last name, major, and are you taking calculus or not? Just those 4 questions. And like I say, in a week, I'll go through, I'll look at all the names. Those people get 10 points for answering the survey. Pretty easy, right? Certainly takes less time than your other homework assignments you have. So please make sure you do that. Again, this is so we can try to make decisions at the school so that we're serving the student population as best as we can, and we can only do that if we have good solid information. And I'll be combining this information with some statistics I'm able to get from the school. They can run certain programs and get statistics for us, and then I will try to build my case for how we should be teaching this class in the future. So if you could do that, I'd appreciate it. Like I say, if you do it right now during class, that's fine too. Okay, we talked about that. Oh, and remember, it's just right under, it's right in your modules underneath the upcoming discussion that we had. So there were 2 discussions that were due. It looks like almost everyone did it. Looks like everyone who's still participating in the class actually did it. That's great. Keep up that kind of work where you're on top of stuff. I know some people, you know, now that we're a little bit in, they start going, oh, this class is going to be easy. Like, this class will sneak up on you, so don't get cocky about it. Just try to stay ahead and finish strong, and you'll be perfectly fine. If you kind of go, oh, everything's going really good, I can kind of pull back and take it easy, this class will get ahead of you very quickly. So just keep that up. Keep up what you're doing where you do the assignments. Be aware you do have one due in, what is that, a week and a half, 2 weeks, something like that. You got another one due, and then try to get this student survey done. That's right, part of the Chapter 2 stuff, which we're going to be talking about today. So you're going to be spending time in this module. Might as well get that student survey one done at the bottom, right? And then I don't think we'll move into Chapter 3 this week, probably next week. I made a list of videos that I'm going to go through in the coming weeks and create for this class. I've got 2 that are going to go into Chapter 2, but I'm probably going to end up showing you that stuff anyway, so if you may or may not need those, or actually maybe we'll talk about them on Thursday, we'll see. Maybe I'll even have the videos edited and posted by Thursday. I got to get my, I haven't been editing videos lately, so I got to go back and update all that software and get all that going. And then we'll get into Chapter 3, and just as a heads up, so after Chapter 3 is when we will take the test. So once exam 3 is finished, that's probably going to happen at the beginning of week 4. So technically the material we cover on the first exam will cover the material through the first 3 weeks, which is up to and including Chapter 3, and then we will have the test at the beginning of the next week there, okay? So just kind of be aware that that's coming, and I will give you a practice test. So the way the tests work, we talked about it a little bit before. I'll go into more detail as we get closer, but I will provide you with a practice test so that you can kind of get a sense of which problems I'm likely to ask you, right? I always reserve the right to change what's on the practice test a little bit, but at the same time, I'm not trying to trick anybody. I'm not one of these teachers that some of these professors take pride in making a really brutal test that, demolishes everybody, and then they think that's good work. I don't really see the point of that. So I'm not looking to put surprises on tests. I'm not trying to trick you. I just want to make sure you can do the problems that are meant that you need to do in order to pass this class. So But there is like 5 questions or so at least. Like, I don't know how many questions will be on the test, maybe 15, give or take a few. But I can give you about 5 that I can tell you are definitely going to be on there, maybe even more, maybe even a few more. Like, you will see a problem like this on the test. Like, I can tell you right now, inverse functions. You're going to have to find the inverse of a function on the test. Might be a rational function. I regularly put those on the test. Finding the zeros of a polynomial, right? That's what I'm going to make a specific video about, showing you how to do that type of problem I'm talking about. You 100% will have one of those on the test. Polynomial division, you'll have one of those on the test. You know, some of these are kind of no-brainers that they're definitely going to be on there. So we can talk about that. And then, like I say, I'll have a practice test posted for you, I don't know, soon. We're not quite there yet, but soon I'll have a practice test posted for you. I graded, so I don't get ahead of myself here, where am I? I graded the 2 discussions that you had. It sounds like I haven't gone to the Discord yet, but it sounds like there is a Discord for students to organize and work together. That's fantastic, right? That's another thing that I've seen work really well. Like, students that used to form study groups in person in the classroom, and then after class they'd go work on stuff together. That works really well. But being an online group, it's a little harder for people to connect. Discord's fantastic, right? Especially since most of you grew up with Discord, you're comfortable with Discord. You know, Discord has a lot of uses and stuff like that. So it makes it real easy, and from the Discord you can organize with each other. You could be in Discord and you could use that to put together some impromptu Zoom sessions. If there's people who want to work on the practice test, once they've done that, you know, get together and work on those problems together, and you can organize it through the Discord. That's great. You can help each other directly through Discord depending on what the problem is. You know, I do kind of recommend some good study sessions are helpful if people want to put those together, but also if you just have a quick question, you might ask directly in Discord. Those are all great ways of doing that kind of stuff. So if you haven't sort of gotten into that yet, I would encourage you to, you know, make your, you know, sort of hitch your wagon to that, and it's going to be helpful. You're going to be able to get some help with the resources that you aren't otherwise able to get help with. I will remind you, there is tutoring on campus. They do have Zoom tutoring available. Maybe even when you're in one of your groups, you do that. So you get you know, through Discord, you form a study group, and then your study group is totally stumped. So then someone goes in and tries to get some Zoom help from the tutors to help them figure out how to do that problem. Great. You're using technology to get this information all figured out. That's fantastic. I encourage you to organize and get that kind of stuff done. So that's kind of where we're going in the near future with things. Let's see, where am I? I did receive 3 homework problems that were requested. So remember, again, even if all I did the whole time we met in these Zoom meetings was just teach you things out of the book, I still wouldn't even get close. I would not even get to 1/3 of the material that we're supposed to cover. So remember, you should always be reading the chapters in the book. One of the most helpful things you can do is read through and understand the examples in the book. Really helpful, right? I'm posting videos to show you how to do stuff, but if you're still unsure, or if you have a homework problem that you can't do, it is extremely likely that there is a very similar example in the book. So I'm happy to go over, like, the 3 people that sent me questions. I'm going to go over those 3 questions in a minute, and I'm happy to do that. I think that's actually great. Please continue to send me the problems that you need me, that you want gone over in class. Sorry, I lost my train of thought there. But yeah, so I'll go over those problems with you, and we'll look at those. Feel free to send me problems to work on, and I'll go over them with you, right? So the bottom line is, remember, I can't cover everything. There just literally is not enough time. But one of the ways that we can help ourselves with that is this thing where you send me a problem. You know, don't just send me every problem that, like, immediately when you have trouble with it. But, like, if you're really stuck on a problem, send it to me, and then I'll go over it in class, and then you'll know how to do that, right? That's kind of more effective than me just guessing and, you know, guessing at which topics you need to see more in depth with. So I'll do that, and that'll take a chunk of time today to go through those 3 problems. And then, let's see, in just a few minutes here, I'll take roll. And then, yeah, I talked about the practice exam. That'll get posted into Canvas probably sometime this week, but I don't really know. It might be early next week. We'll see how that goes. But I'll get that practice exam posted, and you can start working on that. If you are going to work together on the practice exam, here's what I recommend. Print out the practice exam that I get up later this week or early next week or the weekend, whatever. Print it out and work on it yourself. Like, first try to do it by yourself. First see what you can do. There's oftentimes, it's easy to fool yourself when you get together with a group of people and you the group works through all the problems and you're like, great, I know how to do all these problems. When really it's easy to underestimate the amount of help you got from the other people in the group. So what you want to do before you get together with a group in Discord, or from Discord you form a Zoom meeting or whatever, before you get together with that group, look the material over yourself. Try to do the problems yourself, because then you're really going to get a better sense of what you could have done by yourself. And then by all means, work together with other people and help each other through those problems, and then learn how to do those so that you can, those problems so that you can get them right on the test. But just be aware of how much you're doing versus how much the group is doing. And there's nothing wrong with working with the group, but you want to make sure that by the time the test rolls around, you get to the point where you can do the problems by yourself, like without being in the group, right? That's kind of where you have to get at some point. Okay, before we dive into it, let's take roll. Let's get that out of the way. All right, so thank you everybody for getting your names up here. That makes it so much quicker. Let's see, what do we got? Okay, and then if I come over here, we got Okay, so just to make sure I didn't miss anybody here, here's the people that I have missing. Is King A, Eden C, Bridget K, Leanna O, and Eli S. So if any of you are here, please let me know so that I can get you written down as being here. Otherwise, so those of you who are still showing up, like, keep it up. Like, that's kind of the key. You know, as the professor, we see a lot that goes on, and believe me, students always try to convince themselves that they're going to be the one to make some magic formula work, and I can tell you it doesn't happen. The students that do well are the ones that are consistent and on top of things throughout the semester. And so showing up to class, staying current with the homework, all that, those are just the steady steps you have to do in order to be successful. So I know it's tempting to go, oh, I'll let it go a few days. But in a class like, really in any class, math class, but especially in one that's at triple speed, you know, taking it easy, skipping a couple classes, and all of a sudden you're in this hole that you can't get out of. So keep up the good work, all of you that are showing up to class, and keep doing that. Oh, there's a new feature in here. Huh. I'll have to see how that works. What was I doing? Oh, I was trying to check chat. Let's see. Gotcha. Okay. All right. Looks like we're good with roll. Oh, and then, one thing I wanted to mention was, so I updated the grades section on Canvas. So when you do the homework, it should automatically transfer that grade into your Canvas grade, and it will update as you go. Just be aware that there sometimes is a little bit of a lag with some of those dates where, you know, sometimes it won't hold assignments against you that you haven't done. Like here's the thing that sometimes will happen. A student will do the first assignment and they get 100% and they don't try any more assignments. And so it doesn't always update that grade right away. So they're like, oh, I'm not even doing any homework, but I have 100% in homework. This is great. And then it updates and all of a sudden they have a 5% because they haven't done any of the homework. And then they're like, what? My grade went from an A to an F? That's because you didn't do any of the homework. So just be aware there's a little bit of a lag sometimes, depending on lots of factors, between you doing the homework and it being upgraded in the grade book. So just make sure you're doing that. I can't show you the grade book right now because then I'll be exposing everybody's grades. But if you go into gradebook, it should show you that I graded though. You should have scores for those 2 discussions that were due yesterday. And I'm quite pleased at the amount of homework that's being done. This is really good. It would appear that almost all of you are very interested in getting good grades in this class, so that's great. Keep that up. You only got, what, 5 more weeks of doing that, and then you'll, you know, hopefully leave with an A, or at the very least, if, you know, hopefully you get your passing grade. Keep that up, I guess, is what I'm getting at. So, okay, so there's grades. So we got grades, roll call. Talked about the practice exam. Okay, let's do those requested homework problems, and then we will get into number 2, chapter 2, chapter number 2. Okay, so where are we? Oh, I got them right here. Let's see. Oops, I want to close. Let me do this real quick so I don't accidentally expose email here. All right, and then let's see if I can so small, this screen. There we go. Okay, so is this the first one? No, this isn't the first one I wanted to do. Uh-oh. Oh, somehow I have 2 of this problem and not 1 of the other. So hold on 1 second while I pull it up. I'll make sure I don't expose anything here. Let's see, where was this? Would be the one down here. I'll close the email. There we go. Okay, so this was the first question that was sent to me. So this is about the absolute value. So we will talk about absolute values a little bit. I suspect later today. We'll see how time works out, but we'll talk about that a little bit, or we'll definitely talk more about it on Thursday. So many of you learned that absolute value, you kind of learned absolute value in kind of like a sloppy way, and it's understandable when they're teaching you absolute value in, when do you learn that now, like the 4th grade or something like that. It's real easy to think of the absolute value as like, oh, that just makes things positive, or it takes away the negative. Those are things that I hear students say pretty frequently. And the thing is, when you're dealing with absolute values of numbers, that's fine. But as you saw at the end of chapter 1, it's at the end of chapter 1 where we have the, absolute value inequalities. Those get a little trickier, right? Absolute value equations, they get a little trickier to deal with. So you don't really want to think of the absolute value as making it positive, because that's not really true when you start talking about things that are functions. When you take the absolute value of a function versus the absolute value of a number. Luckily for this problem, we're dealing with the easy case where it really is just essentially we're plugging in numbers and then taking the absolute value. But so that's kind of where we're going. So we're given this equation, graph the equation, y equals the absolute value of x plus 3, and we want to let x equal -3, -2, 0, 1, 2, and 3. And then we're going to find the corresponding y values. So remember, this is your basic fallback for how you're going to graph things. Like a large portion of this class is learning sophisticated tools for graphing things, because back when you needed to graph a line, it was fine. You pick 2 points, 2 points determine a line, and then you graph the thing. That's really quick. But once you start getting into more complicated graphs, in order to graph something by plotting points, it's not just 2 points like with a line. It might be 8, 10, 20, 30 points that you have to graph before you really start to see all those curves. You might not recognize it now, but a few chapters from now, you'll look back and go, oh yeah, if I'm going to graph this 4th degree polynomial, I don't want to do it by plotting points, because I'm going to have to plot 40 points or something before I really can see all the behavior of this graph and come up with a nice accurate graph. So we learn more sophisticated techniques, especially things that are going to carry over if you're going on into an applied calculus class, or you need some kind of graphing for accounting or something like that. We come up with those more sophisticated tools that really make your life a whole lot easier when you're trying to graph or understand the function itself. So you can always fall back on this. If you forget your sophisticated tools, you can go, all right, I guess I'm stuck doing it the long way. I'm going to plot some points. So that is, you make a column of x's right here, and then you find the corresponding column of y's, and each row is a point on your graph, right? So that's what we're going to do here. So they kind of do this for us, or did I didn't put that in already, did I? Oh, did I click something? Because that's not even the right answer, right? So basically what you do, you take your x, you plug it in here, the absolute value of -3, so I'm plugging my -3 in for x. The absolute value of -3 would be +3, and then this says, okay, after that, now add 3 again. So in this case, if I plug in -3, the absolute value would make my -3 +3, and then I add 3, and it would become 6. And let's check it. It says, okay, nice work. And then it wants me to keep doing that. So if I plug in -2, I get +2 plus 3 is 5. That's going to make me click every time. Maybe tab will work. Let's see. Nope, tab does not work. Okay. If I plug in -1, so the absolute value of -1 is +1 plus 3 is 4. And sometimes with these, you can start to see a pattern pretty quickly. What's going to happen? Guess what this one's going to end up being? It's going to be 3, right? You can see where the pattern's going. It says, okay, we're going to plug in 1. So plugging in 1 is easier, right? Because the absolute value of a positive number is just a positive number. So that's going to be 4. Then we've got 5. And then plug in 3. 3 plus 3 is 6. Oops. I say, okay, great. Now they want me to pick which of these graphs is the right one. Now there's an upcoming section. I'm not sure if we're going to cover it today or next time. We'll have to kind of see how things play out, if it spills over into next time or not. But you want to become fairly comfortable with recognizing the type of graph that you're dealing with, right? Again, this class is going to be going back and forth between algebra and graphs. Algebra and graphs. We look at the algebra and we learn something about the graph. We look at the graph, we learn something about the algebra. It has to be second nature to you to come back and go back and forth between the algebra and the graphing. Well, one of the things that occurs is it's really helpful if you can start to recognize what certain types of graphs look like. Like if I just showed you a graph, would you be able to recognize, oh, that's a quadratic because it's a parabola. Oh, that's an absolute value because it's a V shape. Oh, that is a third degree polynomial because I recognize that curve that it's got. Oh, that's a sideways parabola. You want to start being able to recognize these because it's really going to save you time in attacking the problems. Because if you can immediately tell, oh, that graph is a parabola, then you know stuff about it. You know, oh, it's a quadratic, so I'm probably going to have to use my algebraic tools for quadratics to figure something out about this thing. So you want to get to that point where when you see a graph, you may not know the exact equation for that graph, but you can recognize, oh, that's some kind of a parabola, and then some transformations have been put on it. In fact, that's what we're going to talk about either later today or next time, is transformations and how to do that. And that's part of that section, is getting to recognize these, what they call them as families of graphs. In other words, every absolute value equation goes in one family. Every parabola goes in one family. So we're just kind of calling them groups. So as you will see here in a couple of sections, every absolute value function looks like some kind of a V shape. It makes like a V shape. Just like parabolas form like a U shape, absolute value functions form like a V shape. Okay, so we look over here and I see some V's, some different places. Well, all you have to do is, this one's not even a V, but I guess you could argue maybe we're just not seeing the part where it curves. Maybe it's part of a bigger V. But for us, we did kind of see where the V is occurring, because see how our numbers are going down and then they're getting up again? That means the low point of our V, oops, it's not letting me show, let's see, is it going to let me move that? Maybe I can show them all at once. I do it this way. That's what I mean, I got to keep resizing everything today. Anyways, we should be able to see the curve in the V. If you look at your points, that should indicate to us. So you're just going to take these points. Each row is a point. So -3, 6. If we go to -3, 6. Oh, well, it's not this one, because this one doesn't have a -3, 6 as a point. What about 1, 2, 3, and up 6? That one might. These graphs are a little small. You got to kind of play with them a little bit. It looks to me like it's probably B. Let's see if I can make that a little bigger. So 1, 2, 3, 6. Wait, that's 10. Okay, it's not this one. It should be at 0, 3. 0, 1, 2, 3. This one's the one I went through earlier. The graphs were a little more clear. 1, 2, 3, 4, 5. So every scale is 2 on this one. Sometimes they'll give you graphs with different scales. So if this is over, yeah, it looks like this is probably the right one. So you're just matching the points over here with the graph over on the right and making sure that they're corresponding. And for all of them, you should be able to eliminate ones that don't work, and it should be that B. Okay, so that's how that one works. All right, so we're just plotting points, matching them to the graph. All right, then we have this other one that has to do with complex numbers. And complex numbers, for the most part, are pretty straightforward, but they do start getting a little weird, like especially with the division. They get a little bit more complicated. Here. So perform the, hold on, before I do this, let me grab a water. My throat's getting all congested. I'll be right back. Okay, so dealing with complex numbers, for the most part, pretty straightforward, but when you start doing divisions, it gets a little bit, can get a little bit weird. So let's look at this and let's walk through it. So it's 6 divided by 2 plus 7 over I, and we have to figure out what we're going to do about that. Okay, so let's create our fraction here, which is 6 over 2 plus, and then another fraction. So we have a compound fraction here, 7 over I. And then I got to figure out which page it's going to show up on. Here we go. Oh, I didn't put it in math mode. Hold on. There we go. So it should look like this. Let's see, I can resize this, make this a little bigger, I think. Okay, so what do we do when we have a complex number, and here it's just I, so kind of a basic complex number, in the denominator of a fraction? Well, you generally want to multiply by the conjugate of the thing. And the conjugate, remember, is just where you take the complex number and you change the sign that's in between it. So if you have a number 2 plus 3i, the conjugate is 2 minus 3i. If you have 4 plus 5i, the conjugate is 4 minus 5i. And sometimes students will go, well, isn't that just mean you multiply by -1? Not exactly, because if you take 2 plus 3i and multiply by -1, you get -2 minus 3i. You're not doing that. You're just changing the sign in the middle. So in this case, we don't have a full complex number. We just have an I. So in that case, you can get away with just multiplying the top and bottom of that fraction by I. So if we have the fraction 7 over I, and I want to multiply by the fraction, you want to multiply the top and bottom by the same thing, but multiplying by I over I will give me the fraction 7i over -1. Okay, and I go, well, how is that helpful? Well, it's helpful in that now that we got that I out of the denominator, we don't have to, we can simplify this fraction, because basically if you have 7i divided by -1, you just get -7i, right? So that means that this whole fraction can simplify to, the whole big fraction, the original one, can become 6 over 2 minus 7i. Right? That's what the new fraction, that original fraction up here, simplifies down to this, because we've multiplied the top and bottom by I. So now I think actually it's going to makes us go through in these little steps. So let's see. Oh, the last one. Oh, it just wants the final answer. Okay, I was thinking of a different problem. So it wants us to write it as the a plus bi when we're done. Okay, so what do you do here when you have something like this? This hopefully looks familiar and you go, oh, that's where I'm supposed to multiply the top and bottom by the conjugate. So we're going to multiply the top and bottom by 2 plus 7i. Okay, so we're going to take this and we're going to multiply by 2 plus 7i over 2 plus 7i. And then you have to figure out what that comes out to. Well, the bottom is going to be a little easier because we get some really nice canceling. That's the whole reason that we multiply by the conjugate, is because it makes everything in the denominator come out real clean. Now, your numerator can be a mess, but that's fine. We don't care if the numerator is a mess. We generally want the denominator to be simplified a bit, right? Just in general. That's why we don't like negatives in the denominator. We don't like imaginary numbers down there. You know, we just want it to be normal. So let's see, let's come back to this in just a second. For the moment, let's look at, we can kind of work out what those would come to. Hopefully everyone's pretty familiar with this by now. So if we have 2 minus 7i and 2 plus 7i, this is going to give us, so you just FOIL it out like you would with a polynomial. This is going to give us what? 4 minus 14, no, 4 plus 14i, then minus 14i. So we've got our outer is 14i and our inner is negative 14i, and then we end up with a minus 49i squared. And I don't, let's see, go ahead and move this over so we can see everything. Oh, come on, you can't give me more room than that. No? Okay. Let's not make it large then. Let's shrink this down and I can fit stuff on here. There we go. There we go. Now it'll fit. So this is what your denominator becomes. Just FOIL it out. Well, the inner terms cancel. 14i minus 14i is 0. So these middle terms cancel. And then look what happens here. We have negative 49i squared, but I squared is negative 1. So negative 49 times negative 1 becomes plus 49. So this becomes 4 plus 49, or what, 53? Yeah, it looks like 53. Okay. All right, so that's what the bottom becomes. And on the top, we have to go, okay, what's the top going to become now? Again, that one doesn't cancel out as nicely. It's a little bit messier, but that's okay. So, in fact, we probably don't even have to write that one out. I think we can just make it work up here. So we'll come back up here and say, okay, this So we want to do this so that on top, when we multiply this 6 times 2 plus 7i, we're going to get 12 plus 42i on top. And on the bottom, we know we're going to get 53. Why is it moving that over? That's... All right, sorry, I tried to make room so I could see it. Now I don't. And now it's getting all weird. Oh well, ignore that for now. So we get 12 plus 42i on top, 53 on bottom. Now this is not the correct form for your final answer. They say specifically in the problem, they want you to type your answer in the form a plus bi. They used to be kind of lax about this kind of thing. Oh, did someone show up here? Okay. But now they're, and they should be more strict about it, where you have to write it in that form a plus bi. So how do you put this in a plus bi form? Because what we have now is not a plus bi, it's a plus b over c. That's not really right. So all you have to do is separate the fraction into two pieces. So this one's going to become your real part, which is 12 over 53. And then plus, then we've got our second fraction, which will become, what do we have, 42i over 53. And then we just have to ask ourselves, can any of these be reduced? Doesn't really seem like it. Doesn't seem like it. So 1253 plus 42i over 53. Let's see if I didn't mess that up. So what is it? 12/53. So 12/53 plus 12/53 plus 42i over 53. 42i divided by 53. There we go, got it right. Okay, so this being a complex fraction, there was a few different things we had to keep track of, but you can see it's actually not too bad. None of the math involved was that that crazy. Just making sure you multiply out those conjugates correctly is kind of the biggest thing. Okay, and then let's see. So then we'll go to this last one, which is solve the radical equation and check all proposed solutions. So a couple things I want to say about that. So this is from that section where it was a review section, and they basically went through and said, hey, let's take all the hard equations from all of algebra and put them together in one section. So they're difficult equations. Now hopefully you learned them already, because they should be prerequisite. You should have learned them previously, but they are complicated, and it's perfectly reasonable if you haven't taken math for a little while. I mean, unless you just finished taking algebra in the spring, then it's easy to forget how to do some of this kind of stuff. So I'm going to work through it, but I want to point out this part too, where they say check all proposed solutions. You just have to do that. I think when we teach you how to solve linear equations, we teach you that checking your solutions is a really good idea, right? And so I think sometimes people get the idea that checking your solutions in mathematics is optional. But it's really not, because once you get above linear equations and once you get above quadratic equations, and so you start getting to the stuff that has square roots in it, rational equations, logarithmic, and all sorts of like more complicated functions. When you solve the problem and you get to the end and you get x equals 7, it is not guaranteed that x equals 7 is actually a solution. And I think a lot of times students have this overinflated like sense of their own ability, where they're like, I'm just going to trust I didn't make any mistakes. Well, there's two problems with that. One is, even if you're really good at mathematics, you make mistakes. I think I mentioned this before. I have a PhD in mathematics. I make mistakes all the time. So doing math, being good at math doesn't mean you don't make mistakes. You do make them. But also, it's built into the system. The way that we solve these equations, you could do everything right and get to the bottom and it says x equals 5, and that does not mean that x equals 5 is a solution, right? Because of the way we solve these high-level equations, inherently we get what are called extraneous solutions, which is the algebra tells us that 5 is a solution, but then when we go check it, it doesn't work. It doesn't mean I made a mistake. It doesn't mean I did something wrong. That's just part of the process. So you just want to understand that checking your work when you solve high-level equations is not just, oh, it's kind of a good idea if you do it. You have to do it. Otherwise, you're going to end up with solutions that don't work, and then you're going to look really silly. Because you didn't know the basics of like why that thing wasn't going to work. You see this a lot with rational equations. You see it a lot with square roots. So let's take this and solve it, because this one does take a little bit of work to get through. So what do we have? Square root of 2x plus 7 equals x plus 3. Okay, so let's go down here. We want to solve. Oops. Solve. I don't even remember, was it 2x and then plus 7? Okay, so square root of 2x and then the plus 7 is outside, and then equals what? X minus 3 or something? X plus 3, okay. And then we're down here now. Okay, so we want to solve this equation. Okay, so here's the steps that you follow whenever you have an equation that has square roots in it. This is like an intermediate problem for square roots. There's ones that are easier than this, and there's ones that are harder. The ones that are harder usually involve multiple square roots. So you might have 2, maybe even 3 square roots in your problem. The good news is you use the same exact strategy. It's just you have to usually do it one time for each square root that's in the problem. So we only have 1 square root, so we only have to do the process once. But if you find an equation that has 2 square roots in it, you do the same exact procedure, but you might go through it 2 times. You might have some problems where you have to repeat the process 3 times in order to get it done. Luckily, this one won't be too bad. We're just going to have a little bit of algebra we have to remember to do over here on the right. So step 1 is to isolate the square root on one side of the equal sign. Okay, so basically that amounts to subtracting 7 over here on the left. So that means I'm going to get the square root of 2x equals x minus 4. So how did this become x minus 4? Well, x plus 3 minus 7 gets us to x minus 4, right? So we get there right now. So we've done step 1. We have the square root isolated on one side of the equal sign. We're good to go with that. Okay. Now what you do is you raise both sides to a power that's going to undo that root. So since we're dealing with square roots, we're going to square stuff. If you were doing a problem with cube roots, you'd cube both sides. But most of the problems are going to be square roots, so we're just going to square things here. So we square to undo the square root. So on the left, you know, it's easy to figure out, well, what do you get if you square square root? You just get what's inside, right? So 2x equals. Now here's where people usually go wrong in this problem. And this is a bad mistake to make, especially when you're, you know, as far as college algebra. But it's a common one. When you look at x minus 4 and you go, okay, now I have to square x minus 4, and people will square each term and go, oh, okay, that's x squared minus 16. Or sometimes people go, oh, well, it's x squared plus 16 because I'm squaring a negative, so that gives me x squared plus 16, right? The answer is no. You cannot, like, the sum of squares is not the square of the sums. In other words, you can't just like pick and choose the terms and square them. What you have to do is recognize that we're squaring the whole quantity x minus 4. In other words, you have to think about it like this. You have to think about it as the quantity x minus 4 squared. And most of you are fine at doing that. You already know how to do that. It's just you forget to do it. And you go, oh, I'm just going to square the x and I'm going to square the 4. You can't do it that way. And you'll see why when we work this out. So what we're going to get here is 2x equals. Now when I FOIL that, so I'm foiling this, remember we can think of this as being right? Because even when it's written like this, I see people square each term. But once you get it written out like this, and people go, oh, I'm supposed to FOIL. Yeah, you're supposed to FOIL, or polynomial multiplication, however you want to think about it, is fine. So then what we're going to do there is we're going to get x squared. Our outer is minus 4x, and our inner is minus 4x, giving us minus 8x. And then we get a plus 16. So see, if we had just squared each term, we would have gotten an x squared and a 16, but we'd be missing that negative 8x in the middle. And the negative 8x in the middle is a big deal. So sometimes the students will go, oh, well, it's close, right? Because I just was missing the negative 8x. Well, it's not really close if you start plugging in values for x. You get completely different answers. So, you know, it's not really close at all, right? But now look what we have. Look what has happened to our equation. We now have a quadratic equation with, here's the good news, no square roots in it. So that procedure where we isolated the square root, squared both sides of the equation, has eliminated the square roots and turned this into a simpler problem of quadratic equations, which we know we can solve one way or another. If it's factorable, we're going to do that because it's easier. If it's not factorable, we use the quadratic equation and get it done that way. So this is really convenient, but we paid for that convenience. Okay, we paid a price for that convenience. Yes, we're going to be able to figure this out, but see how the simplification step we just did here, the price we paid is that by squaring both sides of the equation, it is possible that we introduced extraneous solutions into the problem. Okay, that's what we have to look out for. You always have to look out for that when you're doing these high-level problems, but it's easy to deal with. All we have to do is check the problems at the end. And here's what I've never understood. Many students, like, they just fight checking their problems. Like, they fight checking the work. And they turn in tests and you can see they didn't check anything on it. But that's how you figure out if you got it right or not, is by checking your work. And usually when we check the solutions, it's way easier than finding the solution. So it's like, if you've done 90% of the hard work in finding the solution, why not do the easy 10% in checking it just to be sure? And I know on homework, the computer tells you whether you got it right or wrong, right? So you can kind of get away with that. But on a test, you definitely should be checking your answers, because by the time you figure out you got it wrong, it just means you got a 0 on the problem. So since the test will be written tests. So make sure, especially on exams, when you do a problem, just check it really quick. Make sure you get those points, right? Okay, from here we just solve it. So this should be pretty straightforward then. From here, hopefully. So we're going to subtract 2x from both sides. So we get 0 equals x squared minus 10x plus 16. Which then is going to become, I'm going to go ahead and switch that 0 around, make it equals 0, and let's make it, looks like this is going to be what, 8 and 2? X minus 8, x minus 2. So remember how you solve by factoring. You factor the polynomial, you set the factors equal to 0, and then you solve those. So that will give us x equals 8 or x equals 2 as our solutions. And then real easy to check these. A lot of times you can even do it in your head. Let's see if 8 and 2 are solutions. So let's plug in 8, and let's make sure I didn't make some kind of a mistake here. If I plug in 8, I get square root of 16, which is 4. 4 plus 7 is 11. And on the other side, 8 plus 3 is 11 as well. Okay, great news. 8 worked. See how quick it was to check that solution? It just took a fraction of the time it took to find the solution. But now I know 100%. Like, I even had some doubt when I was talking about it on the screen, because like it's easy to make mistakes, right? But now that I checked 8, I'm like breathing a sigh of relief. Okay, I didn't mess up. I did that right. And then we know that 8 is in fact a solution. Let's see if 2 also works. So if I plug in 2, I get the square root of 4, which is 2. 2 plus 7 is 9. And when I plug in 2 over here, I get 2 plus 3. Oh, 2 plus 3 is 5. So I got 9 on the left, but 5 on the right. Does that mean we made a mistake? No. It means that 2 is an extraneous solution. So if we had just stopped here and said, oh, 8 and 2 are solutions, we would not be knowing what we're talking about, right? We would have done this problem wrong. The solution is really just 8. And you might go, well, why is it a big deal if 2 is not really a solution? Well, what if this is your business and you're going to make a decision based on 2 being a solution and it's not? Your business isn't going to last very long, right? So let's see, the answer is 8. So let's go back and plug that in. The solution set, assuming I did all this right, is 8. Good jobs. Notice how 2 was not in there. So if you don't check it, you'd be putting 2 in there, and it would keep telling you you're doing it wrong. Okay. Oh, and by the way, just in case anyone missed it, this circle with the line through it is what we call the empty set in mathematics. It's the same as no solution. So this is just a fancy way of saying no solution. I kind of wish we still just said no solution in algebra, but they're trying to push high-level concepts like down into lower levels of algebra, things like the empty set, which I think are maybe just overcomplicating things. But that's all that means, is that no solution is that second option. So if you do a problem where you have to click that, it's because you're basically saying there's no solution. Okay? So those are the 3 questions that were sent to me. Feel free to send me questions for next time, and I'll go over those with as much time as possible, right? Because, again, if I just randomly am picking topics and covering them, maybe no one even needs to see that. But if someone sends me a problem, then I know at least that student needed to see that problem, and likely a few of you probably benefited from seeing these as well. Okay, can be helpful. Okay, with that said, where are we with things now? So we're through chapter 1, getting into chapter 2. Okay, so chapter 2, here's a thing I recommend, especially since, so it used to be the case that we gave everybody TI-84 calculators. We used to have hundreds of TI-84 calculators in the division office, and you could go in for free. You could check them out for the semester. So you'd go in, you'd show ID, you'd rent it, and as long as you returned it at the end of the semester, we didn't put a hold on your account or anything. It just, as long as you turned the calculator in, it was just free for you for the whole semester. Graphing calculator can be very convenient, but we're not going to campus. So we don't have the, we don't really have the calculator program right now because this is an online class. But you still need to know how to deal with graphs. Like I said, you need to be comfortable with graphs. If you're someone who's kind of avoiding it, or you're like, I'm just not good at graphing, you won't make it through this class. You won't. So you need to get comfortable with graphing. One way to do that is to use Desmos, Desmos. It is a completely free website. You don't even have to enter your own information. If you want to save things, then you can. But if you're just trying to use it as a graphing utility to help you do your homework and to study, it's completely free. So you just Google Desmos. This will pop up. And you've got Desmos. It's a very easy to use graphing utility, right? And I would, if I was taking this class, I would at all times when I'm doing homework, I would, right next to my tab for maybe even a separate window so I can see both at the same time, I'd have my homework, and in another tab I'd have Desmos, because it's that convenient to go through and use. So this chapter 2 is the first chapter. I guess it came up in the other chapters, but starting in chapter 2, there is lots of graphing, right? Lots of going back and forth between here's the formula, here's the graph, and you have to be able to read those and act accordingly. So let's see, where are we? We've got a little bit of time left here. These are long sections. Right, so I'm just flipping through. I got the new, they finally sent me the new version. Actually, it didn't take them too long, a couple weeks to get it to me. But so I'm not looking, my old edition was a couple editions old, so it was, although it looks like it's essentially the same. I don't think very much stuff has changed. So one of the things, oh, I didn't open up the, let me open up the book so I can show you what I'm looking at here. Let's just go into here, and then we'll open it up here and here. I'm going to move this so I can move it around. Close that. So let's go to 2.1. Oh, and just a heads up about the test while I'm getting myself situated here. So there's the P chapter, which is prerequisite. There's chapter 1, which is essentially prerequisites as well. And then there's chapters 2 and 3. You can expect a fair amount of material on the test. You might even expect like at least one problem from every single section in chapter 3 to be on the test. You can expect a few problems from chapter 2 and a little bit from chapter 1. I'm not going to go pull stuff directly from the prerequisite chapter. That doesn't mean you don't need to know it. It just means I'm not going to test you specifically on like, can you factor this polynomial? I'm going to assume you can factor polynomials, but it's not like you go, oh, well, I don't have to learn how to factor polynomials then, because you need to know how to factor polynomials to do almost everything else in the course. So I won't test you specifically on chapter P, but you got to know how to do that stuff. And it's the same with chapter 1. I'll pull some problems from chapter 1 and put it on the test, but most of chapter 1 is just really setting you up so you can do chapters 2 and 3. So you can expect more problems on the test to come from chapters 2 and 3. All right, just so you know. Okay, let's see. Definition of function. So we have this definition of a function. This is way too small. Oh, that's not. There we go. They changed some of their icons. The magnifying glass used to be to set the font size. Now it's different. Okay, so definition of a relation, and then we've got the definition of a function as well. Wait, what? So the definition of a relation is just a set of ordered pairs. So what's an ordered pair? It's where you've got the parentheses, two numbers, and a comma in between. So the way in which we identify a point on a graph, that's an ordered pair. There's lots of things that fall in the case of ordered pairs. Order means the order matters. If you take the point 2, 4 on a graph, it's not the same as 4, 2, right? They're different points because they're ordered. It's an ordered relation. So basically for any relation, like you can see right here, they've got these ordered pairs right here. These are ordered pairs. There's a set of 4 of them. That's a relation. All right, any set of ordered pairs is a relation. So you just randomly list on a page ordered pairs. There, that's a relation. Okay. The domain is the set of all the first positions. So like in a point, we would think of those as the x values. So in this case, the domain is 0, 1, 2, and 3. That's the domain of our function. The relation is all the second pieces. So the range is all the second pieces. So the range is 187, 212, 225, and 238. That's all that means. I know it sounds complicated, but it, you know, when you first read it, but it's just the difference between the first components and the second ones. Now, we will interpret those in more interesting ways later on, but for now, that's just how you want to think about it. So once we have a relation, we then build a next bigger thing on top of a relation. So the definition of a function, and this is important because most modern mathematics is taught, at least, you know, until you get through calculus and stuff, most modern mathematics is taught from the perspective of functions. So you kind of need to understand what a function is, since that's kind of the way that you know, modern math classes explain all this stuff. So a function is a correspondence from a first set called the domain to a second set called a range, such that each element in the domain corresponds to exactly one element in the range. Now that sounds kind of confusing at first. So what we want to recognize, and it's weird, they kind of lost the story while they were defining these things. What most books do is they define a relation, and then they say, if you take a relation and make one more restriction on it, you get a function. So any function is also a relation, but we're usually more concerned about functions than we are about relations, right? Some of you that go into science and math may deal with things that are just relations and not necessarily functions, but we usually want things to be functions. So let's see if I move this over. So these here are, great. I don't know why Windows always wants to like assume that I want my whole screen to be taken up with something. It's weird how the bar doesn't let me go all the way over. Anyways. So here we have some pictures. If I go up too high, it's going to try to blow it up. Okay, here we have a visual representation of some functions. So here's the first one. We've got 1, 6, 2, 6, 3, 8, and 4, 9. So notice how that's represented over here. The 1 goes to the 6, the 2 goes to the 6, the 3 goes to the 8, and the 4 goes to the 9. So the things that are in the, remember the first elements in your ordered pairs are your domain. So see how the 1, 2, 3, 4 ended up in the domain, and the range are the second positions. So 6, 8, and 9 are in the range, and then we have our values connecting them based on the relationship of those ordered pairs. So what was our definition up here a second ago? Said each element in the domain corresponds to exactly one element in the range. And that's confusing for people because sometimes people think about it backwards. So does each element in the domain correspond to exactly one thing in the range? And the answer is yes. That makes this a function. And some people might be confused and go, wait, I don't think that's right. Yeah, 1 corresponds to exactly one element, 6. 2 corresponds to exactly one element, 6. 3 corresponds to 8. 4 corresponds to 9. So it meets the definition. So you go, but wait, what did it say about exactly one element in the range? Well, that's where we see the second part failing. See, this b over here is not a function. Why? Because see how the number 6 goes to two different numbers? 6 goes to 1 and 6 goes to 2. So now reread our definition and ask yourself if it fits. We want each element in the domain corresponding to exactly one element in the range. Does 6 correspond to exactly one element in the range? No, it corresponds to 2, the numbers 1 and 2, right? So therefore that thing is not a function. All right, let's see if I can get this resized so I'm not in this crazy view anymore. Maybe if I just shrink the whole thing down? I don't know, this is wild that if I don't have it in this massive window, it starts cutting it off. That's what I mean. A lot of times the ebook versions are not as functional as like a normal website. They do have this picture that I want to show you just because it's real common when they talk about functions. So it's this it's a common picture, and it's a convenient way to think about functions, is that it's some kind of a machine, right? Here they talk about a function machine. Basically, a function just takes something and does something to it. So in other words, you have an input, which we're oftentimes going to call an x value. You put it in there, and then some rule occurs and changes your input into maybe the same thing, but maybe something else. It depends what the rule is for your function. So that's all we think of as a function. You put something in, it gets changed into something else. That's a function. The rule could be to double it. And every time you put a number in this doubling function machine, the output comes out doubled. Or it could be that everything you put in gets halved. Or maybe everything you put in gets the square root taken, divided by 7, multiplied by pi, and raised to the e power. Like, there's all sorts of stuff you could do, but it's just some rule that changes your inputs into your outputs. So the inputs are usually called x values or inputs. The outputs are outputs. We also think of the outputs as the y values. We also can call them f of x. So this like f of x right here, that just means the y value. So whenever you see f of x, that's our function notation, but you can also go, oh, well, that's just the y value, because it's literally just the y value. Okay? And then we talked about this a minute ago about graphing functions. They bring up graphing functions. Well, let's talk about evaluating functions too. Evaluating functions is just a fancy word that means plug this thing in. Plug something into it. Okay, so for instance, when they say evaluating a function, if f of x is equal to x squared plus 3x plus 5, evaluate the following. Well, you just take whatever's in the parentheses and you plug it in. So if they say f of 2, you just stick 2 in here. Wherever there's an x, you change it to a 2. That would be easy, right? That'd be 4 plus 6 is 10 plus 5, 15. You're just plugging 2 in there for x. Okay, but what about when it's x plus 3? Now it's confusing because I have x's in there and I'm replacing them with x plus 3's. That's exactly right. Don't overthink it. Just do that. Everywhere there's an x up here, replace it with an x plus 3, and you can see they're doing that right here. The x becomes x plus 3 in these spots, and then you simplify everything and you get your final answer. Okay? So that's evaluating. And then we have, this is the graphing we talked about earlier. So they have kind of a fancy way of putting this together. Remember, we have our x values. And then remember the f of x, that's like our y value, right? We just talked about that a second ago. So here's where they're calculating the y value. So you have a column of x values, a column of y values, and they're just putting the two together to form the ordered pair, which is a point on the graph. So, although we're going to get much more sophisticated than this, you can always fall back on just making a table. We call it a table, an xy table, where you have x's, y's. You plug in your x values, you evaluate them at your function, and you figure out what the corresponding y value is. That's all you have to do there. It's all right. Sometimes I get the hiccups when I'm talking constantly in a class. I gotta drink some water. Vertical line test for functions. So let's jump back over to here to talk about the vertical line test. I think we can show you a little better than just looking at that book. So remember a moment ago, when we defined a function, we said that each input should correspond to exactly one output, right? Well, if you think about it in a graphical perspective, here's an idea of what we're going to be doing this whole semester, is going back and forth between the algebra and the graph. If our x's are our inputs and this is our x-axis, oh, I'm kind of got to resize, sorry. If this is our x-axis and the x's are the inputs, and we're saying that each input for the function should only have one output, then what that means is for each x value, if I go up, I should only hit the graph once. Because if I hit it twice, that means there's two y values. That means it's not a function. So we can translate that into an easy tool called the vertical line test, where we pass a vertical line over our graph, and if it ever hits in two places at the same time, then that proves that thing is not a function. So like right here, this parabola, yeah, looks like that's a function. I'm only ever hitting one point at a time. And then you go, okay, well, what if we made this what if we made it a circle? Well, now I'm passing a vertical line over. Oh, that's not a function, because look, see how I'm hitting the graph twice at the same time? That's not a function, so I can tell right there that's not a function. And then you don't have to have Desmos to do this. You can do it in the beginning when you're first getting comfortable with it. But you just visually in your head pass a vertical, like scan a vertical line across, or use your pencil or whatever you need till you kind of get good at doing this mentally. And then you can decide if the thing is a function or not. Oh, and then remember, x equals a number gives you a vertical line, y equals a number gives you a horizontal line. So that's how you would, and then just letting me scan it across. Okay, so that's what the vertical line test is. Oh, you're going to be asked to identify the domain and range from the graph. So remember, the x values are on, you look at them on the x-axis, and your y values come from the y-axis. So the domain is your x's, and the y's are your range. So if we take something like the following, let's take y equals 2x plus 1, but I'm going to restrict this to be -1 is less than x is less than, say, 5. Okay, so see how we have a restricted graph here? So if I want to get the domain, I'm worried about the x's. So I look at the x-axis. Think about like a shadow being cast by the sun. If it's like high noon, this thing's going to form a shadow right here on the ground. What part of the ground would have the shadow on it? That's your domain. So our domain goes from -1 to 5 on the x-axis. That's our domain. So we would say the interval from -1 to 5 is the domain. Any number between -1 and 5 can be put into this graph. What about the range, the output? Well, there we're going to look at the y-axis. Now imagine a light off to the side casting a shadow against this wall that is the y-axis. Well, we'd see shadow going from -1 to up to 11. So the domain is -1 to 5. The range is -1 to 11. Okay, so that's, you'll get a little practice with doing that on different problems, but it's if you just think of it as like casting shadows, it makes it a little easier to figure out what those are. Oh, and then intercepts are where the graphs intersect the axes, right? So our y-intercept is where the graph intersects the y-axis, so that would be at 0, 1. And the x-axis, which we're gonna find a lot of x-intercepts over the course of this semester. The x-intercept looks like it's -1/2. It's right where the line is going through the x-axis. Okay, They're, y-intercepts and x-intercepts are both really important, but x-intercepts are like really, really important. They're like a big deal. Really helpful for stuff. Okay. And then 2.2 talks about a few different things. Oh yeah, we've got some definitions I want to go over. I really don't like what they've done to this book here. It's like, if I have it where I can fit the thing on screen, then the writing is so tiny, and there's all this wasted space over on the side. It's weird. I don't know. What I will say is I'm not in love with the way my math lab has coded a lot of their stuff. It's not exactly great. But you can follow along here. Okay, so there's some new concepts coming up in 2.2, which I just want to cover, because again, I don't have time to go over everything in depth, but I just want to try to maybe take some of the mystery out of these ideas so that when you're working on them at home, you know, they're not as confusing. Okay, the first one is increasing or decreasing. Now this one is not like, I suspect that each of you has an intuitive understanding of increasing or decreasing. Just think about a bank account, right? Think about your savings account. Would you rather have a graph that looks like this, or would you rather have a graph that looks like this? Well, you'd probably like it if the money in your bank account was going up, right? So you'd like it to be increasing. You want to see an increasing graph, decreasing, and then we have a constant function over here. Now, when people read this, a lot of times they're like, this seems like a way overcomplicated definition. Like, I kind of understand what increasing means, but in mathematics we have to be very careful about how we define functions, because if we're not, what happens down the road is there's a lot of really weird functions out there, things we don't necessarily get into in like a college algebra class, but down the road when you get to those functions, it's not always clear if something's increasing or decreasing. So we're really careful with our definitions to write them out. That way they always can tell us whether something fits our definition or whether it does not. So this is something that's going to happen a lot in the book, is you just need to get comfortable with them using this function notation. And I know it's confusing sometimes for people where they're like, f of x1 and f of x2, what are they talking about? When you see these f of x1s, just remember that's a y value. That's all it is. And the f of x2, it's just a y value. So what we have in the problem is we have x1s and y1s, and then, sorry, we have x1s and x2s, and then we have the corresponding y1s and y2s. So the whole reason we use a subscript is because you can see right here in this problem, we have two x's and we have two y's. Well, how do I know which one's which? Well, notice how the x2 goes with the f of x2, which is the y2, and the x1 goes with the f of x1, which is the y1. So what this is saying is that as your x value gets bigger, your y value needs to get bigger. That's really what all this fancy talk about increasing up here really means. And over here for a decreasing function, as my x value gets bigger, my y value needs to get smaller. Okay, so it's getting smaller. And for a constant function, my y value is always the same. Right, think about, like, if you think about this constant function, what if you had $100 in a bank account and you never touched that money? You weren't earning interest on it, but you didn't spend money, but you didn't put money in it either. Maybe you forgot the account even exists and it's just sort of sitting there untouched forever. It's going to look like this, right? It's going to look like a constant function. And the way you write that function is like y equals 100, right? That's how we write horizontal lines. Okay, so keep that in mind. There is what we call these tests for symmetry. Now, there's all types of symmetry that you can come up with, right? So some of you have probably seen symmetry before. Wait a minute, did I skip a page? Oh, I did skip a page, sorry. I want to talk about this before we talk about symmetry. So we've got our maxes and mins. So a maximum and minimum, and generally what we call a relative maximum or a relative minimum, is what you will sometimes hear called a local max or a local min. So you can have, there's two different types of max and mins. There's global, or what are sometimes called absolute maximum and minimum, and then there's local or relative right? So I know it's confusing. There's these different words, but you'll hear them get used all the time. A relative maximum or a relative minimum means it's a maximum or minimum over a small area, right? So for instance, this is a minimum right here in this little area, but it might not be the minimum of the whole function. And a lot of times I think there's this tendency, I know I thought like this at the beginning, like why do we care about little maxes and mins along the way? Why don't I just find the max or min for the whole function? Well, as we'll see with polynomials, a lot of times there is no max or min for the whole function, but there is local maxes and mins along the way. So if you're trying to optimize where your if you're trying to optimize profit, well, then if your business has to operate somewhere in this zone right here, well, you want to be right up at the top where that dot is. You want to be maximizing your profit, right? Or if this is cost and your business has to live in this area right here, well, you want to minimize those costs so you get the cost down. So oftentimes relative maxes and mins are actually more important than global maxes and mins. It just depends on the problem you're working on, right? It depends on what you're doing. So that's your definitions there. Again, when you see f of a and f of x, you just think of them as y values. This is just saying that for a relative maximum, any value in this area has to be smaller than f of a, because f of a is the peak. Okay. Now, what you want to keep in mind here, because a lot of times people do this backwards, when we talk about a maximum of the function, we're talking about the y value, right? But you need both pieces of information. Like both pieces of information here for this maximum are important. Let's say you were trying to maximize profit for a business. There's two things you want to know. First of all, what is that maximum profit? And then secondly, how many units do I need to sell to reach that maximum profit? Right? I mean, it would be silly not to know either one of those pieces of information. Imagine you go into you work at a business and you're ready for your meeting and there's some work you had to do for your boss before the meeting and he or she wants to know the information and she says, okay, you were supposed to figure out how we're going to maximize our manufacturing for next month. So how do we do it? And you say, oh, well, we can make a maximum profit of $200,000. And your boss says, that's great. We can have a profit of $200,000. Great. How many units do we have to sell to do that? And you go, I don't know. I just have the y value. I just maximized it. I don't really know. That would be, you'd feel silly, right? So the y value tells you what the maximum profit is. The x value is telling you what you have to do to get that maximum profit. And then this, the example I'm giving, it would be, well, we have to sell 50,000 units in order to maximize the $200,000 profit. Then you know both things. You know the goal that is being maximized and you know how to do it. Knowing what your maximum profit can be is pointless if you don't know how to reach that maximum profit. What's the point? If you don't know how to run your business in order to maximize the profit, it doesn't matter that you can make $200,000 if you don't know what's going on. So whenever you're dealing with a maximum, make sure you're paying attention to the x value and the y value and you understand what they represent. Because I see a lot of students, like, they kind of memorize this technique for how to find a thing, but they don't really know what it means. You don't really want to do that in a math class because, first of all, it's kind of wasting your time. What's the point of like learning a bunch of stuff that you don't understand? It's not really going to help you down the road. If you're going to take the time to learn it, you might as well actually understand it, right? So that's the maximums and the mins. Now, yeah, okay. I was looking where the new blue box is. So what I started talking about a minute ago was symmetry. There are different types of symmetry in the world. Now, most of you, back in grade school, we'd see the symmetric picture where if you folded it over, it was the same on both sides and it would match up. And that is a type of symmetry, but there are many types of symmetry. So we can have symmetry with respect to a line, which is kind of the one I just discussed. If you take the picture and fold it over and the two sides match, that's symmetric with respect to a line. You can have symmetry with respect to a point. You can have rotational symmetry. What if you have a shape that when you rotate it 180 degrees, it matches itself? That's a rotational symmetry. There's many, many different types of symmetry that can occur. And one comes up in this section. Now, what I will say is, I think this book makes a little bit too big a deal out of symmetry, but it's one of the topics we're supposed to teach in this class. And I think it's important to know it, but the book unnecessarily brings it up a lot of times. The reason we care is these functions called odd and even functions. But the thing is, very few functions in this course are going to come out to either be odd or even. What I can tell you is there's a high degree, well, what I'll say is in the past, I put these problems on a test pretty frequently. So you probably want to know how to do them. So what does an even function mean? Okay, so and the reason these are big deals, any of you who are going on to learn trigonometry, then classifying even and odd functions in trigonometry is like a big deal because it'll save you a ton of work. If you understand the symmetries of your trig functions, it's going to cut your work way down, right? But we don't do trigonometry in this class, and most of the functions we deal with are not symmetric. So you'll see later in the book when they give you directions, they'll say check if it's even or odd, but like none of the ones you ever do will be even or odd. So you don't even have to, it doesn't come up, but you do need to know what these mean. So here's where it gets confusing again. The function f is even if f of negative x equals f of x for all x in the domain. So see how again we're looking at the algebra and we're connecting it to the graph. Okay, so what does that mean if we look here at this thing? See if I can make this slightly bigger without wrecking the thing. Okay, so f of negative x equals f of x. Remember, those are y values. So f of some x value is just a y value. We're saying the y values match when the x values are opposite. So what that means is if I plug 2 and negative 2 into a function, into an even function, I'll get the same y value. If I plug pi and negative pi into an even function, I'll get the same value back. Okay, that's what they're showing you here is when they plug in 3 and negative 3, see how you're getting the same y value? That's this type of symmetry, and they call it an even function. It's symmetric with respect to the y-axis. So if you had this as a piece of paper and you folded it right along the y-axis, that blue line is going to match up right on top of the red one, right? That's a type of symmetry. That is an even function. And it can be very useful when it comes up. It comes up all the time in trigonometry. It'll come up a couple times in here, but it's not going to come up that much. So that's how you tell the difference between, that's how you tell if something's an even function. If I put in an x value and the opposite of that x value, do I get the same y value every single time? If the answer is yes, like this parabola, it's an even function. Okay. So what does an odd function mean? And it looks the same. At first you might go, wait, isn't that the same definition as the thing above it? No, if you look at them both carefully, this one says f of negative x equals f of x. This one says f of negative x equals negative f of x. So what does that mean? That means if I take the y value for this negative x, that should be the negative of the y value for the x. In other words, in this case, if I plug in a 2, what do they have to plug? Oh, they didn't. It's kind of neither. But if you plug in a 2 and a negative 2, your output should have the same number but opposite signs. See how when we plug in a 2 here, we get 8. When I plug in a negative 2 here, I get negative 8. So same number, opposite sign. That's what we call an odd function, right? And there's actually a couple ways you can classify the symmetry of an odd function. You could actually, like, think about this graph right here. Think about what I talked about a minute ago. Take that and right at the center, at the origin, just rotate it 180 degrees. You get the same function again. So it has a rotational symmetry to it. So it's a different type of symmetry than you're used to, where you fold a piece of paper over on itself. There's no really way that you could fold this piece of paper to see the symmetry. You have to think about it in terms of rotating it. So it's a rotational symmetry. So graphically, you can look at these things pretty quick. This is an odd function because it's reflecting across the origin. This is an even function because if I folded it in half on the y-axis, it would line up. This is neither. So most things that we run across in this class will be neither. They are not even functions. They are not odd functions. They are neither one. And then they have a little piece over here telling you how to identify them. It takes a little bit of work, but so that's what that means. That's what our even and odd means for the for graphing those. Okay. Then we have a thing that gets hammered. Oh, two things we want to do. Yeah, okay, great. Should have time to talk about both of those. Okay, so first let me point out one thing to you, and then we're going to talk piecewise functions, because I know that really confuses students. So first let's talk about this, the definition of the difference quotient of a function. So the difference quotient is f of x plus h minus f of x over h. This is a really, really important thing in mathematics. It's basically, the calculus is sort of based on this thing right here, and in large part is based on this. This difference quotient is really important in calculus. What it gives us, it's really just a fancy version of slope, right? Remember your slope was y2 minus y1 over x2 minus x1? Well, in a real fancy way, we can rename that and call it f of x plus h minus f of x over h. Is there a picture on the next page? There is not. They don't have a good picture to describe this. But basically, if you look at the top, remember I keep saying how these f of stuff, f of whatever is really a y value? So you can see we're subtracting two y values on top. Well, what is this h? H is just what we've renamed the difference between the x values. So it sounds kind of silly, like why, if it's just slope, why do we have this much more complicated formula? Well, for one thing, we're transitioning from algebra towards calculus, right? That's kind of what college algebra is kind of getting ready people for calculus. In calculus, you very rarely use the slope formula. You always do it in terms of functions. So this is that similar one. So this difference quotient is needed for some of the most important topics in calculus. That's why they're teaching it to you now, because you need to be able to, if those of you who are going on to calculus, you need to be able to deal with difference quotients and do algebra with the difference quotient in order to do those problems that are in calculus. So that's why they're just getting you comfortable with that difference quotient. For real easy problems, the difference quotient's not that hard, but they can get hard fast. If I give you like even a cubic polynomial, a third degree polynomial, calculating the difference quotient is a pain. It's just annoying, right? So it depends on what type of problem you're doing. And then half of first semester calculus is just figuring out, first you learn how to take the derivative using the difference quotient, and then half the class is how do I avoid having to use the difference quotient, right? But like you still have to do it from time to time. So that's why they make a big deal out of it now. So just make sure you're comfortable with the difference quotient. And if we can go over one next time, if somebody sends me a problem with the difference quotient, we can go over it in class. If everyone's good with it, then we'll spend our time on other stuff. But again, feel free to send me problems and we can go over those. Okay, next big thing I want to talk about, this is really important, is piecewise functions. People really struggle with piecewise functions, like in a way that's like, there's just something in some people that just don't seem to be able to wrap their brain around a piecewise function. But once you get it, it's one of those things that once it clicks, you go, oh, that's actually not even hard. Why did I ever think that was hard at all? It's like super easy. But some people, like, they just can't get their brain through the notation in order to understand what that piecewise function is. So I want to talk about a piecewise function. I'll show you how to deal with them on Desmos, which will hopefully allow you to work amongst yourselves to work these problems out, okay? So what is a piecewise function? What does that even mean? Well, think about it just a normal function. So you've got, y equals 3x minus 4. This is a rule to our function. You recall earlier when I showed you that picture of the, there was that picture of the function machine that's in our book, and I called it a rule. Basically, that's what a function is there's a rule that you put an input into this function machine, and the rule tells you what to do with it. The rule might be to double it, or to square it, or to take the square root and subtract 7 and multiply by pi. Like, you can come up with all sorts of different rules, but that's really what a function is. It's a rule that says, take your input and do this thing to it. Well, we've always dealt with one rule function so far. Well, in real life, things are more complicated than that. Like, things oftentimes don't always follow one exact rule forever. Think about if you're a parts buyer at a company, and your job is to go out and buy parts. so that you need for your manufacturing plant, so that you can't manufacture things if you don't have the parts for them. So they call that a buyer. So your job is to make sure that you always have enough parts on hand so that the manufacturing company, or the manufacturing wing, your warehouse, can just keep pumping out parts, right, of whatever you make. Well, a lot of times when you buy parts in mass, you pay a different price depending on how many you're buying, right? It's kind of the Costco thing where like you get a really good price on stuff, but sometimes you got to buy this like massive jar of mayo or whatever, right? Like if you buy things in large quantities, you tend to get better prices of those things. So a company might have 3 different rules. You call up and you say, okay, I'm the buyer and I need to buy, part A, I need it for next month. And they say, and you're supposed to buy them, and they go, okay, well, it depends how you go. How much is each part? And they go, well, it depends how many you buy. So this is very common. If you buy, say, 1,000 of the part, you're going to pay a certain price. If you buy 2,000, you pay a little less per piece. So they're basically saying, hey, if you buy more, we're gonna knock the price down a little bit so that we're incentivizing you to buy more product, because it's a lot easier for me. If I need to sell 2,000 units and I can sell 1,000 to you, and then I have to go find another buyer to buy 1,000, it's a lot easier if I can just get you to buy the 2,000, right? So they market it so that if you're willing to buy more, we'll give you a better deal, right? So you're spending more overall, but you're spending less per unit, which means that increases your profit of whatever you're building, the less you pay for your parts. So they might say, okay, if you buy 1,000, let's say it's a washer, like the little flat piece of metal with a hole poked out, that kind of washer, not like a washing machine, but a washer. And they say, okay, if you buy 1,000 of these, we're going to sell them to you for 10 cents a piece. But if you buy 10,000, we're going to sell them to you for 8 cents a piece. And if you buy 100,000, we're going to sell them to you for 5 cents a piece. So now you have to sit down as the buyer and think, okay, well, we're obviously going to get the best price if we buy 100,000, but do we have money for that? I don't know. I don't think we have that in the budget right now. So you have to figure out at what price to buy that thing. Well, what I just mentioned was 3 different rules, right? If X is between 0 and 1,000, you pay 10 cents. If X is between 10,000 and 1, what did I say the next one was? Oh, sorry, it was 1,000. So if you buy from 0 to 1,000 of these washers, if X is between 0 and 1,000, then you pay 10 cents per piece. If it's between 1,001 and 10,000, you pay 8 cents a piece. If it's 10,001 to 100,000, you pay 5 cents a piece. That's 3 different rules. Well, maybe we want a function that incorporates those 3 different rules. That's all a piecewise function is it says, instead of having 1 rule, let's have more than 1 rule. Okay? Now, so what you have to do, though, with the piecewise function is figure out, well, how do I know when I'm supposed to use which rule? And they generally tell you. So here's your notation for a piecewise function. Is that the one I want to use? Yeah, good enough. They don't have that many examples. Actually, let's use this one over here. Let's use this one. So this is how we write a piecewise function. So see how it starts off with the f of x, just like we're used to for functions. But then over here, instead of just saying f of x is equal to x plus 2, there's 2 options. Sometimes the rule is that you take your input and you add 2. And sometimes the rule is that you take your input and you turn it into a 4. Okay, well that's great. There's 2 different rules. How do I know which rule I'm supposed to follow? Well, they tell you right next to it. If x is less than or equal to 1, then you follow the top rule. If x is greater than 1, then you follow the bottom rule. So it's actually really easy. You go, okay, I need to know 2 things. I need to know what the rules are, and I need to know when to use them. Well, they tell you that. Here's the rules right here. Here's when you use them. So what if I wanted to stick 5 into this function? Well, then I would look, is 5 less than or equal to 1, or is 5 bigger than 1? Well, 5 is bigger than 1, so I'm in this category right down here, where I'm in this part. So that means that the rule I use is I turn things into 4s. So when I stick 5 into this function, it comes out of 4. Okay. What about when I want to stick 0 into this function? Well, then I come over here and I ask myself, is 0 less than or equal to 1, or is 0 greater than 1? Well, this time it's the top rule, because 0 is less than or equal to 1. That means I'm supposed to take my input and add 2. Okay, well, 0 plus 2 is 2, so now my output is 2. So don't, I think people wrestle with the notation and try to figure it out. Don't overcomplicate it. There's just 2 things you need to know. What are the rules of this function, and when am I supposed to use them? And they're both here. Here's the rules, here's the when you use them. But it's all based on the x value. You're comparing the x value to these conditions right here, and then that tells you which rule to use for the actual function, but you're still just doing the same thing. You're just plugging a number in and evaluating it, but you have to figure out which rule to use before you do the evaluation. So that's all it means, is you've got your different scenarios, and then you list when they can happen, and it looks like this. Okay. Now sometimes you're going to get, sometimes your piecewise functions will match up and connect to each other, but see how this one doesn't? See how there's a gap? Yeah, sometimes you get a gap. They don't have to meet up perfectly. Anything can happen with a piecewise function. And then you get the extremes of piecewise functions. These are what we call step functions. Those of you who are going into more sciencey type stuff, you'll deal with these from time to time. You see we have a whole bunch of disconnected pieces. Each one of these is essentially a different part of a piecewise function, right? There's sort of a different rule for it. So that's really what's going on with piecewise functions. I'm almost out of time. And you can graph them as well. If you want to graph the condition on a piecewise function, some of you probably saw me do this earlier, but you may not have caught exactly what I was doing. So let's say we have y equals 2x minus 1. Here's a function, and when Desmos makes it, they just go forever, right? But what if I want to reduce this to match the conditions of the problem that I'm working on in the class? Then what you do is you put some curly brackets, and then you put the condition for your x values. Remember, this part over here is always comparing the x values to decide which rule to use. So over here in Desmos, I can just say, well, I want my x's to be between -1 is less than x is less than 5. And see how it's only graphing the line for the x values between -1 and 5? Yeah, that's that piece of a piecewise function. And then we could have another one that was, y equals 9. But in this case, I only want that to be where x is greater than 9. Oops, that's not what I meant. X is greater than 5. There we go. See how they match up nicely? Sometimes that happens, but they don't have to, right? We could just as easily could have this, where they don't match up. That's totally allowable. There's nothing that says they have to meet nicely in the middle. Okay? And right as we run out of time here, in 15 more seconds, that gets us through 2.2. 2.3, honestly, should be review. Everything from 2.3 you should have learned in a traditional algebra class when you took a traditional algebra class, which may have been a long time ago, but all of that should be review for you. So at this point, I would say you definitely should be able to get through 2.1 through 2.3. We will talk next time a little bit more about 2.4. Actually, you can probably do almost everything in 2.4. So you probably reliably could get through most of 2.4 on your own. Send me problems if you need me to go over some questions next time. Then we'll get into transformations, which if you want to work ahead and try to get through 2.5, Desmos is a lifesaver on transformations. It's going to help you see these transformations so much quicker. I don't have time to go over it, but I can show you that next time. And then we'll go over the rest of Chapter 2. And we're kind of seeing, Chapter 2 is that section where it starts to ramp up. The first half of Chapter 2, like I say, you've seen a lot of this before. By the time, but not all of it, even and odd functions are new, piecewise functions might be new. By the time we get to the second half of Chapter 2, things have definitely ramped up to where we're solving for inverses and composition of functions. It gets a little bit more complicated. So, that's where we're at. I will see you in a couple days. Please work on the homework so you can send me questions if you need any, so I can go over those particular problems. Otherwise, we will continue moving ahead. Okay? All right, thanks everybody. So as always, I'm going to shut down the YouTube stream, but I will stay, until people are done asking me questions. I'll stick around in Zoom for a few minutes. If anybody wants to talk to me, you have questions about the class, you need help with a homework problem, whatever you want, hop into Zoom and I'll help you out. Okay, thanks everybody. I'll see you later.